So we're going to look at molar mass of compounds or elements, either way, to convert between the number of grams of a sample and the number of moles of a sample. Okay? So basically, I can look at any mass of a sample and I can calculate how many moles are in that sample. Okay? And vice versa. I can look at a half of a mole of a substance and also tell how many grams are in that substance, just using the molar mass. Okay? The molar mass is what we call the conversion factor between grams and moles. Okay? So if we want to compare grams and moles of an element or of a compound, we have to use that molar mass. All right, so I'm going to give you basically some steps as to how we do this, but it's going to make more sense once we start really applying it and once we see a practice problem. Okay, so I'm going to write out a couple steps that you can use to get through this process, but I think it will make a little bit more sense once we start applying that. Okay, so that's up to you if you really want to write down the steps or not. Okay, we're going to use the T-chart system, which we used already when we did conversions of the metric system, right? So the first step in a T-chart is to write what you know. That's the same for these conversions, right? If we start with 50 grams and we want to find out how many moles are in that substance, the first thing that we do is write 50 grams and make our T, right? Do you remember T-charts a little bit? Okay, write what we know. Set up our units so we cancel out. So if we want to get rid of grams, grams needs to go diagonal, right? When we want to get rid of units in our T-chart, they need to go diagonal from each other. Unit you're converting to goes on top, what you're getting rid of from, or what you're getting rid of goes on bottom. That's the rule most of the time, right? We see a few exceptions to that, but that's really the rule, okay? What we start goes on top, what we want to get rid of goes on the bottom. That works 99% of the time, okay? This is something that's important here. The mole always gets the 1 in our conversions. Okay, always. Because we're telling how many grams are in 1 mole of that substance, right? That is our molar mass. So if we look at oxygen, the molar mass of oxygen is 16. So that's telling us in 1 mole of oxygen, there is 16 grams of that substance. Okay, so the mole always gets the 1 in our T-charts. Okay? The gram, when we're looking at our T-charts, always gets the molar mass, which you find from the periodic table. Okay, so again, these steps will, I hope, make more sense when we start looking at examples. But here's the basic process to get us through these. Okay, after that, do the math. Make sure your units are canceling out. Multiply across the whole top, divide by the whole bottom. Okay, that's the math for the T-chart, right? Multiply across the whole top, divide by the whole bottom. Try some here. How many moles are in 74.2 grams of a compound LiCl, right? So lithium chloride. How many moles are in 74.2 grams of this substance? So basically, we're looking at a sample of this lithium chloride that happens to weigh 74.2 grams. And we want to find out how many moles, right? Because moles is the unit that scientists like to use to display a quantity of something. Okay? So we like to work in moles. So that's why we bother doing these conversions at all. Okay, you might say, why don't we just leave it in grams? Moles gives us a consistent quantity across the board. So when we compare two substances, let's say lithium chloride and water, we want to compare quantities of those substances. It won't do us any good to compare the quantities in grams because the elements within those compounds weigh different things. So it would give us a kind of a skewed comparison. If we compare in moles, that gives us an even playing field in terms of comparison. Okay, so that's why we work in moles a lot. So let's take a look at our problem here. We always write what we know to start. So 74.2 grams of lithium chloride. It's essential here that you keep the units and you keep the compound in the T-chart. Okay, eventually we will start dealing with more than one compound. Okay, we'll have to compare two different compounds, and if you don't include what compound it is, then you're going to get confused. Okay, so keep that in there. We want to go from grams to moles, so grams needs to go on which side? Top or bottom? Grams of lithium chloride goes on the bottom, and moles of lithium chloride goes on top. Okay? And we said the mole always gets the 1. Okay? So now we look at this column of our T-chart right here, and we say how many grams of lithium chloride are in 1 mole of lithium chloride? Okay, how would we find that? Yeah, we find the molar mass of this compound. Okay, so that's what we need to do next. Lithium chloride has 1 lithium atom and 1 chlorine atom. Lithium I'm probably going to keep at about 6.9. Okay, just because it's in the range where you could maybe get away with rounding, but I'd just keep it. Okay? And chlorine is 35.5. So we need to add those two together. Did I do that mental math right? That's good. Okay. And what are my units here for molar mass? Grams per mole. Okay, so now I need to plug this into my equation. I'm saying right here that in 1 mole of lithium chloride, there are 42.4 grams. Okay, grams per mole. Are we on the same page with how those numbers got there? Okay, mole always gets the 1. No matter what you're comparing it to, mole gets the 1. So now we multiply across the whole top, divide by the whole bottom. If you just look at your starting amount, could you expect that we're going to have more than 1 mole? Right? Isn't the mass of our starting amount greater than the mass of 1 mole of that compound? Yeah, so we should expect that we should have more than 1 mole. Okay? And so we take 74.2 divided by 42.4, right? Because we would multiply across the top, which is multiplying by 1, divide by the bottom. Somewhere around 1.5, 1.75, larger than 1.5, I'm sorry. 1.75, and what are our units here? Okay, lithium chloride, but what are the actual units that go with the compounds? Moles. Moles of lithium chloride. Moles is just MOL. If you just abbreviate with an M, that means meters. Okay, so moles is MOL. The reason that we know that moles is our unit here is because they cancel, right? Grams of lithium chloride cancels diagonally right there. So we're left with moles. Okay, simple enough? We on the same page? All right. Let's try this one. How many grams are in 0.42 moles of magnesium nitrate? Okay, we're starting with moles now, and we're going 2 grams. So I always start my T-chart with what I know. 0.42 moles of MgNO3 parentheses 2. And then I make my T. These T-charts are simple. They're just one step. Okay, we're going to get into them where they have, maybe 3 or 4 steps to the T-chart. If I'm going from moles to grams, which needs to go on the bottom right here? Moles, good. Moles of MgNO3 2. And grams goes on the top. Moles always gets what? The 1. And then we're going to tell how many grams is in 1 mole of that substance. Right? We leave all the math until the end. Don't try to work ahead. All you're doing is looking at this particular column and you're telling me how many grams are in 1 mole of that substance, which means you're going to calculate the molar mass. Okay, how many magnesium atoms do we have? 1 times 24.3. Good. How many nitrogen atoms do we have? 2. And its molar mass is 14. And how many oxygen atoms do we have? We have 6, right? And its molar mass is 16. Okay, so add that all up. All right, what did we get for our molar mass here? 138 or 48? 48.3. Okay, grams per mole. And that means we're going to plug this in here, 148.3 grams per 1 mole. Okay, multiply across the whole top, divide by the whole bottom. Would we expect our mass to be greater than or less than the molar mass? Less than, right? Because we're only dealing with less than half of a mole. Okay, so that means the mass should end up less than half of that 148. Okay. Cece, what'd you have for your final mass in grams? 62.286. So I'm just going to round that to 62.3. Okay? And again, I'm okay with wherever you round to. I usually like at least 1 or 2 decimal places. Okay? And our units here are what? Grams. Just grams, right? We're looking for how many grams? We got rid of the moles, so our units there are just grams. Yeah, that's right. You still do have to label with the element or the compound. Okay. Very good. Let's try these last 2 on your own. All right, as I was walking around, I'm seeing most people on the same page. Okay. Our final answers should have ended up here. We've talked about Avogadro's number, but I might not have told you that's what it was called. Okay, Avogadro's number tells us the number of moles in comparison to the number of atoms or molecules. Okay? So Avogadro's number is 6.022 times 10 to the 23rd. We talked about that being the number of something in a mole. I don't know that I gave you necessarily the name Avogadro's number. It's important for you to understand that Avogadro's number is not just atoms per mole, right? It could be anything. Okay, it could be the number of atoms, it could be the number of compounds, it could be the number of molecules, it could be the number of baseballs, it could be the number of roses, it can be the number of anything per 1 mole, okay? Because 1 mole always equals that number. Okay, just like a dozen of anything equals 12 of anything, this is just a much bigger scale of that. Okay, so it doesn't always mean atoms per mole, but most of the time that's the reason we use this number. We don't see a mole of anything in the real world. Okay, so when we're looking at these comparisons, the number of water molecules or the number of hydrogen atoms or whatever, that we're going to use that number to determine that's how many of that particular compound or particular element are in 1 mole. Okay? Molecules per mole, base. Okay, we already talked about that. You don't have to write that part down. We're just talking about the mole in terms of what we know that it is. Okay? This one says 6.0235. So obviously there's some variance in the number of moles, but yeah. Get it? See, it's equal to a mole over here. Oh. Okay. Let's see what. Yeah. I must have been feeling funny when I made this. Okay. Guacamole. Get it? Ha, ha. Gosh. If only I wrote these things, I'd be a millionaire, right? All right, let's try this one. If we have 0.73 moles of lithium, how many atoms are in that sample? Okay, this is the same T-chart problem. Okay? So I actually already have my little T-chart drawn out here. But I'm always going to start by writing what I know. Okay, if I have 0.73 moles of lithium, how many atoms are in that sample? Would we be expecting the number of atoms to be greater than, less than, or equal to Avogadro's number? Why greater than?
Less than because it's not a whole mole.
It's less than because we're not looking at a whole entire mole. Okay, so we should expect the number of atoms to be smaller than Avogadro's number. Are we seeing that relationship?
Yeah.
Okay, we're starting with less than a mole. That means I would have less than Avogadro's number worth of atoms. Just like if I said I have 9 baseballs, is that greater than, less than, or equal to a dozen? Less than. Okay, it's the same type of relationship that we're looking at here. Okay, so we have 0.73 moles of lithium. If I want to get rid of moles of lithium, where does it need to go?
Bottom.
On the bottom, so moles of lithium. And what needs to go on top? Atoms of lithium. Good. And if we were looking at water, right, it would be molecules, not atoms, because we're looking at the whole entire compound. Okay? So now we do the same thing. Moles gets the 1 again. Because we don't know how many moles are in one atom, right? That'd be a tiny, tiny, tiny fraction. Instead, we say how many atoms are in 1 mole of anything. Avogadro's number, right? In 1 mole of any substance, there are this many atoms. So it does not matter if we're looking at oxygen or carbon or water or salt or anything. There's always Avogadro's number worth of atoms in 1 mole of that substance. Okay? So we multiply across the whole top, divide by the whole bottom. Mm-hmm. Right, and your calculator probably says E23. What does the E mean?
To the 23rd power.
To the 23rd power. So E on your calculator means times 10 to the. So when you're using Avogadro's number, I would really encourage you to use the EE button. Uh-huh. So this should be 0.3 what? 0.39. Or 0.4. Okay, that's fine. I'll just leave it at 3.9, but yeah, I understand. I accidentally plugged in 0.72 instead of 0.73. Okay? When you're using your calculator, I would strongly encourage you to use the E button. Okay, so when we're looking at the number of atoms or molecules or something, you should get a huge number for your answer, right? Times 10 to the 22nd, 23rd, 24th, whatever, okay? It's going to be a big number. If we're looking at the number of grams of something, it's going to be pretty reasonable. Could be, it's a pretty wide range. If we're looking for number of moles of something, it should be a very reasonable number. Usually between 0 and 10, usually. Okay, grams can get up there, but usually when you're dealing with moles, you should be looking at between 0 and 10 moles, usually. Okay, because moles is usually a really reasonable number. Okay, so if you took the time to count 8.23 times 10 to the 23rd grains of sand, okay, which everyone does at some point in their life, okay, we want to find out how many moles is in that amount. If you had to guess, greater than, less than, equal to 1 mole? Greater than. Good. Because that number is greater than Avogadro's number. Okay? So let's start by writing what we know in our T-chart. So 8.23 times 10 to the 23rd. You can just put grains here. It doesn't have to be anything specific. Okay? And does it matter that it doesn't give us a chemical formula here? It doesn't matter, right? When we're looking at atoms or molecules, it doesn't even matter what compound we're working with. Because in 1 mole of that substance, there's going to be 6.022 times 10 to the 23rd atoms, or grains, or molecules, whatever that is. Okay? So we'll put grains of sand down here on the bottom. Mole goes on the top. Moles of sand. The mole always gets what? The 1, and then how many grains are in 1 mole?
6.022.
Good. Very good. So here, when you divide by Avogadro's number, that's where it becomes essential. You either use the E button or you use parentheses. If not, your calculator is going to mess it up. Okay, so you need to either use that E button or you need to use parentheses around the whole Avogadro's number. Our answer to be a little over 1 mole. Did your calculator agree with you there?
Yeah.
Good. Okay. And Rachel, can you tell me what you got?
1.3 or
1.4. Okay. 1.4, and what's our units? Moles. Moles of sand. All right, how are you feeling about those? But what's the connecting factor? What do we have to stop at in between grams and molecules? We have to use moles. Okay? It doesn't mean we have to do 2 separate T-charts. It just means that somewhere we've got to go to moles in between those. We don't know how many grams are in 4.89 times 10 to the 24th of a substance, right? We don't know how many grams, but we can find out how many moles, and then we can find out how many grams. Okay, so we've got to have that be our middleman. We're using the same T-chart format, except our T-chart now basically has 3 spaces to it instead of just 2. Okay, and I'll show you what that looks like here when we start an example.
Where did they come up with Avogadro's number?
A person discovered it.
Yeah.
Discovered that each particular sample, he just determined that each of them, 1 mole of that substance always had that many molecules, so he got to name it after himself. Mm-hmm. As far as the experiment he did to get to that, I don't know that off the top of my head. Okay, so as you look at these problems, I want you to start kind of thinking about the big picture here. Okay? Do we expect this to be greater than or less than 1 mole? Probably less than, right? We know the molar mass of salt roughly. Probably less than, which means your final answer should be coming out less than Avogadro's number. So just kind of keep that in mind as a way to check yourself. So let's look at the math here. The first thing we do is plug in what we know. Okay, and then we make our T. Can we go directly from grams to molecules? No, we need to go grams to moles. Okay, moles always gets the 1. And how many grams are in 1 mole of sodium chloride? Right, that's where we go and find its molar mass. So go ahead and do that now. You can do it now, you can do it after you finish plugging in the rest of your numbers, that's fine, but we'll go ahead and do it right now. Okay, do we agree with molar mass there? You might have had 58.4 if you kept it at 22.9, but okay, I round that up to 23. Okay, which means 58.5 goes right in here for the molar mass. So now I've canceled grams, and I'm left with mole. Is that what I want my answer to be in? No. So I need to get rid of moles, which means it goes on the bottom, right? It goes diagonal. And up on the top goes molecules. And there's no really way to shorten molecules. Moles always gets the 1. And how many molecules are in 1 mole of any substance? Okay. So now we've canceled moles. We've canceled grams. And we are left with molecules of sodium chloride, which is exactly what we want. Okay, multiply across the whole top, divide by the whole bottom. Are we expecting a big number here or a small number? Big, right? We're looking at number of molecules. So don't miss in your calculator where it says e to the 23rd, right? Otherwise, you're looking at our final answer being 1.49 or 1.5, 1.4. Yeah, we're in that range, yeah? Okay. If you leave this off, if you don't see that in your calculator, then you're telling me there's 1.5 salt molecules in 14 grams, right? Which is no good. And our units here are, yeah, molecules. Molecules of NaCl. Okay, do we see now that we have 3 sections of our T-chart? It doesn't change the math that we're doing. We just have to add moles as our middleman. Okay? So when you're doing these problems, you really need to take a step back and think, should I be expecting a huge number here, or a reasonable number, or I don't know, or, you can kind of check yourself. So we expected our number to be less than Avogadro's number because we started with less than a mole. And is that what happened?
Yes.
Yes, good. Okay, so you can go back and double check yourself in that way. So if you get stuck, you can take a look up here. Okay.